Thanks for having me here to speak. Today I'm going to be talking about compositional recurrence analysis, or CRA, which is a technique for generating numerical invariants that I've developed along with a bunch of collaborators. Really, it's maybe a family of analyses that all operate on the same basic principle. They all follow the same recipe. And what I'm going to talk about today is not really the nuts and bolts of numerical invariant generation, but rather this recipe for building abstract interpreters. Before I get into the recipe, I want to talk a little bit about what compositional recurrence analysis does. So there's kind of two key features, the first of which is that it generates invariants in a very rich assertional language. So it can infer linear, polynomial, exponential, and logarithmic relationships between program variables. It can infer equations as well as inequations. It can infer modular congruences. It supports exact disjunction. Right, so this is a numerical invariant domain, so we don't reason about things like memory, but as far as numerical properties go, there's a lot happening here. The other key feature is that it's compositional in a strong sense of the word, which is to say that the way that CRA analyzes a phrase in a programming language is by analyzing each of its subphrases independently and then composing the results. So there's lots of things to like about compositional analyses. They have greater potential to scale. They can be parallelized easily. They can be applied to incomplete programs where you don't have all the code. They can be applied incrementally. If you change a small section of code, you don't have to reanalyze everything. There's also one thing to not like in particular, which is that compositional analyses can't make use of context. So contextual information is something that we really like to exploit in program analysis. So in sort of conventional abstract interpreters, we propagate information from the initial states forward so that when we're analyzing a program fragment, we know which states we might be in when we're executing it. In software model checkers, we typically propagate information from error states backwards so that when we are analyzing a fragment, we know what we want to prove about that fragment. And if we subscribe to this particular religion of compositionality, we're not allowing either of those things to happen. The analysis of a phrase in the programming language cannot depend on its surrounding context. So it's not clear that this is a good idea, but experimentally we see that it is. So here we have a benchmark suite of 150 safe linear integer benchmarks, which is kind of the common intersection of what all these tools are capable of reasoning about. We have some abstract interpreters over here, which are fast, but out of the box, not so accurate. The refinement-based model checkers are more accurate because they incorporate an abstraction refinement loop, but the cost of that abstraction refinement loop is that it yields non-termination for some cases, which makes it slow down. CRA, as you might expect from a talk that's advertising CRA, is both fast and accurate. All right, so you should take these experimental results with a grain of salt. Don't take them too seriously. I'm just bringing them up early in the talk so that I can convince you that maybe something interesting is going on, so that when I start talking about category theory in a few minutes, I don't put you all to sleep. Okay, so we here at the Static Analysis Symposium are all interested in how we can answer questions about the behavior of software. And one particular view of this field is that we can separate it into sort of a practical side where we say, okay, everything's undecidable, let's figure out how to answer questions often enough to be useful. And then we have a theoretical side where we say, okay, everything's undecidable, but why? So we try to find where exactly this decidability barrier lies. So we propose a bunch of abstract models of computation that actually have decidable properties. And so the main theme of today is that we're going to put all of these nice theoretical results to work on the practical side. And so this is sort of the key to the success of CRA and the theme of today's talk. We're going to use these abstract machines to analyze real programs. All right, so I'm going to begin by talking a little bit more about the structure of CRA. Then I'll talk about this recipe for computing numerical loop invariants. And then I'll present a bunch of examples of this recipe, and in particular, describe CRA as one instantiation of this thing. All right, so at a high level, what compositional recurrence analysis does is take in a program, say written in this grammar that you don't have to look too carefully at, and compute a transition formula, which is a logical formula here in the theory of nonlinear integer arithmetic that has two distinguished vocabularies representing the pre-state and the post-state. So the unprimed variables represent the values of program variables before executing a computation, and the prime variables represent their values after. So for example, let's take a look at this program that's going to count from x equals 0 to some symbolic constant n, and at each step it's going to non-deterministically choose to either increment y or z by x. Something we might want to prove is that after executing this computation, x is going to be exactly n. We might want to prove that because we're always adding a positive value to y and z increase over this computation. And we might want to observe that regardless of whether I increment y or z by x, I'm always incrementing the sum, so I can describe the exact dynamics of the sum of y and z by this quadratic formula. Okay, so this is a transition formula, right? There's nothing exotic about this. This is standard fare for interprocedural analysis. It's a function summary, right? It's a relationship between the pre-state and the post-state. What's a little less standard is that I'm going to take this sort of to the logical extreme, and I'm going to do nothing but compute summaries. Right, so I'm not going to just summarize functions. I'm going to summarize loops. I'm going to summarize conditionals. I'm going to summarize single instructions. The only thing that exists for CRA is summaries. So what this analysis looks like is kind of an effective denotational semantics, by which I mean that it's a semantics that we can compute, but which is approximate. Right? I'm computing properties that are satisfied by the program, not an exact characterization of what that program does. And we compute the transition formula by recursion on the syntax of the program. So in the base case, we have an assignment instruction, and we can compute a transition formula simply by saying x prime is equal to e, and every other variable doesn't change, so we have y prime is equal to y. We compute a transition formula for a conditional by computing transition formulas for each branch, conjoining with the appropriate guards, and then taking the disjunction of the result. We can compute the transition formula for a sequence by computing transition formulas for each subprogram and then taking the relational composition of the result. And while loops are, of course, where all the interesting things happen. So everything else is just encoding the exact semantics of the program into logic. Loops are where all of the computation happens. So for the rest of the talk, I'm just going to talk about loops. Just as an aside, I'm going to present this analysis on structured programming languages because it's easy, but it extends to arbitrary control flow using the framework of algebraic program analysis by Tarjan, and it can also be extended even to recursive procedures. So it's a fairly general paradigm for describing program analyses. Okay, so now we want to figure out how to compute transition formulas for loops. So the assumption of compositionality demands that a transition formula for a loop is computed as a function of its transition formula for its loop body. Right, so the input to my analysis is going to be a transition formula representing a single step of the loop, And the thing that I want to compute is a formula that over-approximates the transitive closure of that formula. All right, so let's take this transition formula for the loop body and look at what it looks like geometrically. So we have 3 program variables, so we can imagine a state as being a point in 3-dimensional space. If we begin at the origin, then we have 2 possible successors corresponding to either incrementing y or incrementing z. If we take another step, then we have 4 successors, and so on and so on. So the way that we're going to approximate the dynamics of this loop is by considering its image under a linear transformation. So I'm going to map this 3-dimensional space onto a 2-dimensional space by saying the first dimension corresponds to the x dimension of 3-dimensional space, and the second dimension will correspond to the sum of y and z. Now, if we look at the image of this computation under the linear transformation, well, the origin maps to the origin. Both successors map to the same abstract successor. All 4 of the next successors map to the same abstract successor. And more generally, the image of the transition formula under the linear transformation corresponds to an affine transformation in 2-dimensional space. All right, so affine transformations are great. We've been studying them for hundreds of years, and we have a pretty good idea of how to analyze their dynamics. So in particular, there exist methods that I can use to compute a symbolic representation of the k-fold composition of this function f. So if I apply this function f k times to its initial argument, vx and vy plus z, then that corresponds to this sort of symbolic affine transformation, symbolic in the loop count k. Now I'm going to take this closed form, and I'm going to map it back into 3-dimensional space by kind of applying this linear transformation in the reverse. And what I get is a transition formula that over-approximates the behavior of my loop. All right, zooming out, what we have is some class of abstract machines. Here we've used affine maps, for which we know how to compute the reachability relation. So there's some function, which I'll call CL, that maps each machine into a formula that represents the transitive closure of the transition relation of that machine. So we also have some mechanism for taking a transition formula and approximating it with an abstract machine. And the way that I'm going to analyze a loop is essentially just to compose these 2 things. So there's some details here that are being omitted, but this is sort of the high-level picture. By composing this reachability relation computation with the abstract machine computation, what I get is an over-approximation of the transitive closure, and I use that to analyze my loops. And so there's no fixed point computation going on. No explicit fixed point computation going on. There's still a fixed point. There's no widening. This is the whole story for how you analyze a loop. All right. So let's dive a bit further into the specification of this abstraction function alpha. Right? Clearly, there should be some relationship between the transition formula and the abstract machine that approximates it. And the way that I'll formalize that is by simulation relations. So a simulation between 2 transition systems A and B is going to be a binary relation, which is, first of all, total. So for all A states, there's a corresponding B state that simulates it. And if A is simulated by B, and A can take a step to some A prime, then B can take a corresponding step to B prime, and B prime will simulate A prime. So returning to our picture here, the simulation is just this purple line here. It's you can think of this linear transformation as being a binary relation between the state space of the transition formula and the state space of the affine transformation, where they're related exactly if it's the image under this linear transformation. All right, so this is a simulation relation that happened to be a function, but that needn't be the case. So here's another affine transformation that simulates our transition formula. This time it's 4-dimensional, and I don't have a good LaTeX package for drawing 4-dimensional figures. But you can see that the first two dimensions correspond exactly to the 2 dimensions we had earlier, and the two new dimensions are effectively symbolic constants. Right? So the action of G is just the identity on these 2 additional dimensions. And the relationship between these 2 new dimensions and the transition formula is given by these inequalities. They say that Ly is a lower bound for y, and Lz is a lower bound for z. So I'm going to be able to use this to prove that y and z are increasing throughout the loop. Okay, so that tells us that, yeah.
So here Ly and Lz, they're constants, right? I mean, this is just the identity. I mean, you're just saying that they don't change, right? But
yep.
It seems like you've lost the upper bound part.
The upper bound part.
Ly and y is lost when you go to that matrix form.
It's lost when you go to the matrix. What do you mean by that?
I mean, the transition relation has Ly is less than or equal to y, but then down there, the red part does not talk about y at all, right? And then it's only Ly.
Sorry, the upper bounds are not part of the presentation? Yeah, there's... so actually, let me step forward a couple slides, and then I'll maybe be able to answer that question in a better way. But the high-level picture that I want to paint here is that not only is the class of abstract machines important to the types of invariants you can compute, the simulation is also sort of an essential part of the story. So the reason that I'm able to prove inequalities rather than equalities is not because of the machine. I'm using the exact same class of machines. I'm exploiting the power of the simulation relation. Okay. So the principle that I'm going to exploit is this well-known idea that if the transition system B simulates the transition system A by some simulation S, then that S is also a simulation between the transitive closure of B and the transitive closure of A. And the reason for this is simply because I can stack a whole bunch of these boxes together. And what this means really is that I can over-approximate the transitive closure of A by this formula, right? So the idea is that A is going to be my transition formula. It's going to be something for which I don't know how to compute the transitive closure. B is going to be my abstract machine. It's something where I do know how to compute this transitive closure. And because I can compute this transitive closure and I compute these simulation relations, I can compute the entire right-hand side of this formula. This is a computable over-approximation of my transition formula. All right, so the intuition is that if I start at A, that I am only allowed to step from A to A prime if it's also possible to sort of use the simulation to step into my abstract machine, apply a bunch of transitions of my abstract machine, and then use the simulation relation to sort of step back out. And I think this is sort of the answer to your question, Aus. The relationship between the abstract state and the concrete state is restored by the second application of S. So what this is saying is that this Ly, which was a lower bound for y at the beginning, is also a lower bound for y at the end. So what that means is that y prime is going to be greater than or equal to y. Yep.
Is that related to weak simulation? It is also called weak simulation?
So weak simulation, so if we allow multiple steps of B to be matched to a single step of A, that works as well, yes. I'm not going to be using that form of simulation, but you could certainly reformulate everything in a more general context by using a weaker notion of simulation. Yeah, but I guess kind of the key idea is that we're not just applying the simulation once, we're sort of conjugating the transition relation of B by the simulation, and that's what's going to give us an over-approximation of the transition formula. All right, so looking back at this picture, this transition formula here is exactly what you get by conjugating this by the simulation after applying some simplification steps to eliminate the existential quantifier. Okay, so now we can describe kind of the high-level recipe. So there's two parameters that, as an analysis designer, you need to fix. The first is some class of abstract machines. So I talked already about affine maps, but there's lots of different abstract machines for which we already know how to compute the reachability relation. So solvable polynomial maps are something I'm going to be talking about in a little bit, but also difference boundary relations and octagons and integer vector addition systems. You can invent your own. The second thing that I'm going to fix is some class of simulations. Right, I'm not going to allow my simulation to be arbitrary. In particular, I need my simulation to be representable by a formula. So some examples of simulations that are currently used in CRA are identity relations, where we enforce that the state space of the abstract machine is exactly the same as the state space of the concrete machine. Linear relations, which we saw in our affine map example, and polyhedral relations, typically sort of restricted polyhedral relations. All right, so if we fix those two parameters, then the recipe is as follows. First, we need to find some closure operator that maps each M machine into a transition formula that over-approximates, or sorry, that gives us an exact characterization of the transitive closure of that machine. Second, we need to be able to define an abstraction function that takes any transition formula and produces some abstract machine that simulates it. And so there's some way to identify a simulation for any f between f and alpha of f. Finally, the way that I'm going to define my abstract transitive closure operator is this formula that we've already seen. All right. So this is the missing component of our compositional analysis. Once we define this iteration operator, we're done. This is a fully fledged program analysis. All right. So now I'd just like to talk a little bit more about this alpha, right? I've given you sort of a specification for what alpha ought to do, but this is sort of an under-specification. We'd like to get a better structure, or a better idea of how to actually design one of these alphas. And I think a clarifying view for this is to phrase everything in the language of category theory. So if we fix a class of simulations S and a class of machines M, then we can form two different categories. The first is going to be the category of transition formulas, where we take as objects transition formulas, and arrows are simulations belonging to S. And the other category is the category of abstract machines, which we'll call M, in which the objects are M machines and the arrows are simulations of the same kind. Right. So we are used to thinking of abstraction in terms of order theory, and this category theoretic setting is really not so different. So here's the beginning of a little dictionary that we can use to translate between category theory and the more familiar order theoretic setup. So these category theories these categories are just standing in place of where we would ordinarily use partially ordered sets. But instead of having a binary relation, we're going to have these arrows. So the one machine simulating another is not a binary proposition. There's content on that simulation. So we want to be able to distinguish between different simulations between two different machines. Right, so the whole reason that we're using category theory is just to be able to make those kinds of distinctions. So you might think of a category theory, the category is really just like the Hasse diagram, except I'm going to use labeled edges instead of unlabeled edges. So my category theoretic generalization of a monotone function is going to be a functor. And my category theoretic generalization of a Galois connection will be a pair of adjoint functors. So probably you can already see where I'm going here with this. Just like in order theoretic abstract interpretation, a Galois connection is going to give us a characterization of when we have best abstractions. In this setup, adjoint functors will tell us when we have a best abstraction. Okay. I mean, this is kind of an uninteresting example, but imagine that this Ly was not less than y, but less than z, and this Lz was less than or equal to y rather than b, right? So it represents exactly the same information, but it's a different morphism. Something that represents different information would be that both Ly and Lz are less than or equal to y, right? So this would be an example where I have a worse simulation.
What's the motivation for using the category theoretic formulation, then stick to the order theory?
It's so that I can distinguish between these different types of simulations, right? There's content in the simulation, whereas, so let's see. It doesn't really make sense to just say one abstract machine is better than another abstract machine. It only really makes sense to compare two abstract machines paired with simulations, right? You need to understand exactly how that abstract machine is an abstraction of your concrete machine in order to make a comparison. Okay, so let's suppose that we have our two categories, TF and M, and we have a functor gamma, which is our concretization functor. Given some abstract machine, it just computes a transition formula that represents a single step of that machine. Right, so gamma isn't really interesting. You can think of gamma as sort of a witness that this M is really kind of a subcategory of transition formulas. Right? Like every machine has some representation as a transition formula. That's what gamma is saying. So a left adjoint to gamma is a functor that goes in the opposite direction, computing a best abstraction of M, and there's an interesting relationship between these two functors. Just like in a Galois connection, there's an interesting relationship between the adjoints. So the part of this relationship that we're most interested in this setting is that there's a natural transformation from the identity functor on transition formulas into the composition of gamma and alpha, which really just means that there is some way of associating, for every transition formula F, a simulation that goes from F to gamma of alpha of F. Right, so all of this is saying is that the abstraction of F must indeed be simulated by, must indeed simulate F. But it's not just an arbitrary simulation, it's sort of the best simulation in the sense that if we have some other machine M and a simulation from F to gamma of M, then there exists a unique simulation from gamma of alpha of F to gamma of M that makes this diagram commute. So thinking about this in order theoretic terms, what this is saying is that gamma of alpha F is really sort of the least upper bound for all abstractions in M of F. The content of the fact that this diagram commutes says that the way in which gamma of M is an abstraction of F is sort of compatible with the way in which gamma of alpha of F is an abstraction of F. All right, so there's a similar diagram on the other side, but this is the diagram we really care about. Right, this is what gives us sort of the recipe that we saw before, some way of given some F, finding a simulation from F to the abstract machine that approximates it. So there's a whole bunch of nice properties that come out of having a left adjoint to gamma. In particular, we have monotonicity of the analysis, which is to say that if I have more accurate information about a loop body, then it means I will have more accurate information about the loop itself. So if I added a bunch of additional preconditions, that means that I'm going to have a better abstraction of my loop. It means that if I make syntactic modifications of my loop body and produce an equivalent formula, I'm going to produce an equivalent abstraction of the loop. Right? So we have all of these nice robustness properties that make it easier to reason about the behavior of our program analysis. And right, we can't expect that best abstractions always exist. They don't, but they do happen more often than you might expect. All right, so for the rest of the talk, I'm going to present some examples of this recipe. Yep. Yes.
Yeah, okay. So so that summary was sort of critically dependent on getting that affine transformation right. And you can imagine that if then that summary was plugged into a summary further up, you might have a different loop structure there, which suggests that at the next stage up, you might need a different affine transformation.
Mm-hmm.
Is that right?
Yes. Yeah. So this will happen at every step. We'll compute a completely new simulation and a completely new affine transformation.
Okay. So I got the impression you have a fixed transformation. You don't have a whole hierarchy of them.
Yes, right. So this is sort of important from the assumption of compositionality, where right we want to only be inspecting sort of the current loop at a given time in order to compute the abstraction of it. So yes. At every step, we'll compute a totally new abstraction. And we'll always compute a best abstraction in a way that I'll describe. All right, so our kind of warm-up exercise is Cartesian relations. So this is our class of abstract machines. We have a transition relation that's really just the Cartesian product of two sets. So think of P as a precondition, Q as a postcondition. We can go from any state that satisfies the precondition to any state that satisfies the postcondition. It's really easy to compute the transitive closure of such a relation because it's already transitively closed. It may not be reflexively closed, so we just add the disjunct that y might be equal to y prime. And that's our closure operation. Let's fix our class of simulation relations to be identities. So we're going to have exactly the same state space. And then we can compute a best abstraction for a formula f by computing a precondition by existentially quantifying the post-state variables, and a postcondition by existentially quantifying the pre-state variables. Right, and this is the best abstraction we can have for a transition formula as a Cartesian relation. Does this make sense? All right. A little more complicated. Let's look at sums. So this is a class of abstract machine where the state evolves simply by adding some constant vector b to the state. Again, it's pretty easy to define a closure operator. We existentially quantify some loop count k and just say that k must be greater than or equal to 0, and the post state is equal to the pre-state plus k times our additive vector b. Let's fix our class of simulations to be polyhedral relations of this particular form. They just say that the state of the abstract machine must be a lower bound on some linear transformation of the state of the concrete machine. And then we can compute best abstractions as follows. So first, we're going to introduce a fresh vector of variables, which is called delta. And we'll assign delta to be equal to the difference between the pre-state, the post-state and the pre-state. So we're just defining a whole bunch of difference variables. Then we're going to existentially quantify the pre-state and the post-state of the transition formula and compute the convex hull of this formula. So the convex hull can be computed using an SMT solver and using some polyhedral relations, or polyhedral operations. So what we end up with is a constraint representation of the polyhedron, which looks like alpha, or say A delta is less than or equal to B. And we can read the best abstraction directly off of this, this half-space representation. Namely, the A is going to give us the simulation between F and the sum machine, and the additive vector is just going to be the B. Everyone happy? All right, getting a little more complicated and also a little more hand-wavy. Let's take a class of abstract machines to be affine transformations where the only eigenvalue of the transformation matrix is 1. The reason that we care about this spectral assumption is because actually affine transformations are not that well understood. They're complicated. In particular, many of the decision problems surrounding affine transformations are not known to be decidable, in particular Skolom's problem. Under the spectral assumption, we have a really nice way of computing the transitive closure. So in particular, the dynamics of this machine are going to be expressible in polynomial arithmetic, and we can do this by first computing the Jordan normal form of the matrix, and then it's sort of for free from that. So let's fix a class of simulations. I'm going to say linear transformations. And I can compute best abstractions using the following method. So first, I'll extract the affine hull of the formula using an SMT solver. I can just use point sampling. The affine hull is going to be just a characterization of all affine equations that are entailed by that formula. And then there's some linear algebra tricks that I can play to put those equations in the correct form. I'm not going to explain what those linear algebra tricks are, but this is the idea. It's really not so different from the delta trick that I used in the lossy sums picture. All right, my last example will be solvable polynomial maps. These are polynomial maps, so think of it as a sequence of polynomial updates where we don't have nonlinear circular dependencies. So here's what I would call a circular dependency, because the value of x in the post state depends on the value of y in the pre-state, and vice versa, but that dependence is linear. In this second example, we have a quadratic dependence of x on y and a quadratic dependence of y on x. That's not allowed. Okay, so we're making sort of this maybe artificial seeming syntactic restriction, but that's okay because we're always going to just be computing an abstraction of the loop. Right? We don't expect the loop to actually be of this form. We're going to compute the best abstraction of the loop of this form. although it's not the best abstraction. We'll get to that in a bit. I'm going to explain even less about how to compute the transitive closure of these relations. There's a bunch of ways of doing this. Maybe the high-level intuition is that solvable polynomial maps are sort of fundamentally actually linear. You can simulate a polynomial map by a linear map by adding a bunch of dimensions that represent nonlinear terms. And then you can sort of play the standard tricks. So one method that we've developed for computing transitive closure of these relations is an operational calculus-based method. I'm not going to explain anything about what this does. All you need to know is that the closed forms involve polynomials and exponentials and some additional operators. So these operators, I'm just going to treat as uninterpreted functions. They have a meaning, but understanding that meaning is very difficult. So that runs into Skolom's problem again. I don't really understand how to analyze these operators, but my SMT solver can just treat them as an uninterpreted function, and I can compute an over approximation. All right, let's fix a class of simulations to be linear simulations again. But we see that best abstractions aren't computable because we're operating in nonlinear integer arithmetic now. So there's no way to distinguish between, sorry, we can't distinguish unsatisfiable from satisfiable relations in nonlinear integer arithmetic, so we can't hope to compute non-trivial best abstractions. Right, so this is the first case we've seen where we can't compute best abstractions, but we can still sort of use these guiding principles that's given to us by the category theoretic framework to compute an approximating solvable polynomial map. All right, finally, with all of this set up, I can describe two papers on one slide. So the FMCAD paper, which is the original compositional recurrence analysis, is really just sort of a reduced product between the Cartesian relations, the unit spectrum affine maps, and the lossy sums that we've seen before. So this allows us to generate polynomial equations and inequations, and the Cartesian relations allow us to maintain information about the guards of the loop. So by reduced product, I want to distinguish between a product, which would be just computing these abstract machines independently, and then computing the transitive closure, and then conjoining the results. The reduced product can have more interesting relationships between these abstract machines. So in particular, they can all synchronize on the number of times that you execute this loop, and it allows you to create non-trivial correlations between the state spaces of the different machines. So the POPL18 paper is basically the same thing, except unit spectrum affine maps have been replaced by solvable polynomial maps, which allows us to analyze the behavior of loops where even a single iteration is going to be governed by nonlinear behavior. All right, so that's more or less it. I presented this recipe for building abstract machines. So next time, or for building abstract interpreters. So next time you want to develop a numerical invariant generator, maybe you can think about following this alternate recipe for building abstract interpreters. There's lots of interesting work to do in this space. So first of all, if you're interested in theory and want to develop new kinds of abstract machines, go ahead and do it. Maybe we can find some way of actually using that. And there's also a lot of interesting questions here involving theorem proving and abstract interpretation, and how do you compute best abstractions of transition formulas. All right, that's it. Thanks.
Okay, we have some time for questions. There's one over there.
So maybe there's something about compositionality I don't understand here. Suppose that I have a nested loop. And so in my inner loop, I'm saying I'm putting in polynomials and I'm getting out exponentials. Right? So then in my outer loop, I'm putting in exponentials and getting out something. I mean, it doesn't seem like the same analysis applies to the outer loop.
That's a great point. That's true. So the transition formula that comes out of the analysis of the abstract machine may not be of the same sort that I know how to compute best abstractions from. So in all of these cases, we can compute abstractions of those transition formulas, but they may not be best. Right? So the best is usually with respect to sort of the linear fragment, and then there are heuristic procedures for extending it beyond that. So in the particular case of exponentials and polynomials, we will indeed throw out the exponential relationships that we infer on the inner loops, as long as we can't say that those exponentials are really symbolic constants. So if we have some sort of polynomial update to an exponential, then we'll lose that information. We won't be able to represent that in our abstract machine, and so we'll lose some aspect of the dynamics of the inner loop.
More questions? Andreas?
So your program
Can you take the mic, please?
So your programs didn't seem to have guards. I mean, the examples you showed, how do you handle guards? As your statements.
So guards, well, okay, so first of all, from the perspective of loop analysis, these Cartesian relations are how we handle guards. So the reason that we're able to prove that, for example, I have to go back to the beginning. That x ends up at n at the end of this program is exactly because our Cartesian abstraction is going to allow us to maintain the information that x must be strictly less than n in the pre-state of the loop and less than or equal to n in the post-state of the loop. And conjoined with the negation of the guard, that's going to give us the x prime equals n. But if you're talking about more generally, like how do you handle conditionals, then they're simply encoded into the formula. So we don't have an explicit assume because I've used this structured programming language, but assume is something that's supported by the analysis.
The star it also could be a guard.
What's that?
The same example. The star. If you could have a numerical guard here,
Yeah.
how do you deal with it?
Okay. So there's a few different answers to that question. So if it's something that I don't really understand how to analyze, so for example, let's say that it's y less than z. Sure, okay, y less than z. Yeah, that's actually a good example. I'll get exactly the same abstraction out of this if I have y less than z. No, that's not quite true. I won't come up with exactly the same abstraction because I'll be able to infer that some post-state relationship holds between y and z using the Cartesian relation.
Take x is positive,
If you,
then you have only one branch, and the equations are completely different.
yes, and the SMT solver will see that branch is unsatisfiable, and I won't compute anything for it, right? So the SMT solver will help me out there. There are other interesting examples, like if x is less than n over 2 or something, and this is sort of a phased loop where I'm going to first start out by executing a whole bunch of iterations of the y gets y plus x, and then start executing the z gets z plus x.
Yesterday we learned that SMT solver, they don't give always the same answer. They get stuck, they get unknown, not yours.
So we only use the theory of quantifier-free linear rational arithmetic. So all support for nonlinear reasoning is built into an abstract domain on top of everything. So we sort of use the SMT solver to sample a point in this sort of over-approximation of the formula, and then use the abstract domain to do more precise reasoning about the nonlinear relationships.
So, Patrick, you had another question? No? Oh. No, it's okay.
Can you comment more about your second slide where you placed the CRA and the other analyzer? So something more about your experiments?
What these programs do? Yeah. So these are all micro benchmarks. They're drawn from OLA, which is benchmark speak from the Dilligs and some others, I think. That involves a lot of modular arithmetic. C4B is resource-bound analysis examples, and SVComp is assorted things. These are all simple programs. They're all very small, but tricky. What do I mean by?
Intervals.
Yeah, but so there is a analyzer built into to CRA that does sort of a pre-analysis. So this is not the most sophisticated abstract interpreter in the world. It does some widening with thresholds. It does delayed widening, but it doesn't do like trace partitioning or anything like that.
Okay, next question.
So your idea is to abstract transition systems, and you improve over the past because in model checking they were taking homomorphic abstraction, which is completely stupid. And Matthew Might was essentially having the same idea, but with also homomorphic abstraction, essentially. And but he can go higher order. I'm not sure you can go higher order.
I certainly don't know how to. Yeah.
And so the correspondence in your case is a simulation. And Ronzato and Tamparo, they approve that simulation, they are abstractions. So this means that there is a generalization where the correspondence will not be a simulation. And I was wondering if you have some idea on that. And I have a second question. Related because they will cut me if I don't ask my second question now. There are some properties that are not expressible on the transition system. One example, where you need the full trace, like dependencies or things like that. You need to remember in which order things happen. And so the second question is, you could do a simulation between traces, not transitions. So would you have an idea to make two generalizations? So one without simulation, but Galois connection or something more general, and the other not transition system, but traces.
So I'll answer the traces question first. So yes, you can definitely do that on traces. So a particular example of this is that data flow analysis has been done in this sort of algebraic framework by Tarjan. So there the relationship is certainly a relationship on traces because the state doesn't capture enough information to determine, say, reaching definitions. So yes, that generalization works. Although combining it with sort of numerical invariant generation is something that I certainly haven't done. I think that would be interesting. The other question is or generalizations of simulation. I'm afraid I don't really I'm not familiar with what you're talking about.
The fact that you have a simulation is important, and you fail if you don't have one. So what I don't understand is where you fail if your relation is not a simulation relation. Why you require that? Why is it so important?
So the simulation is important in order to prove that the transitive closure of the abstract machine over approximates the transitive closure of the concrete machine. Oh, I see. Okay, yes.
So it's not the reason why you use simulation. You have another one.
I see.
I want to understand this one.
Okay, fair enough. Okay, so I have one case that maybe we could talk offline where we have sort of a weak simulation, which isn't really super worked out, but I think that this is something that could be generalized at least to sort of multi-step simulations. Beyond that, I would say that it's much easier to think of how to design these best abstraction routines if you think about simulating a single step. Like the simulation, restricting yourself to a simulation or a class of simulations provides guidance in how you're actually going to compute this thing. So it's certainly possible that with generalizations of simulation you might have similar guidance, but yeah.
Okay, so very last question with a mic, please.
What happens if you consider bi-simulation instead of simulation? Everything collapses to some simple case?
What happens if you think of bi-simulation instead of simulation? I don't think it collapses to being uninteresting, but it's certainly less general. So I believe, let's see. For functional simulation relations, it should be equivalent. So the thing that you gain in using simulations rather than bi-simulations is the ability to have more general abstractions. But I would also say that bi-simulation doesn't help you. Like it doesn't help me. I can't compute a more accurate information about a loop by considering bi-simulations. Right? So if you think of this in terms of the category theoretic setup that we saw before, by saying I'm only interested in bi-simulations, you're effectively looking at the subcategory of each of these categories in which you only look at the bi-simulation relations. And the left adjoint to the concretization functor is going to always give you a worse result, right? Because there are fewer simulations to look at.
Okay, I'd like to thank Zachary for his nice talk on answering the many complex questions from the audience. Thanks.